We're running. Okay, so welcome to the USB, the Urban Sciences Building, and our National Green Infrastructure Facility, where we've got lots of kit and lots of experiments, and this has been on one of the videos we've already loaded up for you. So, because we've had to cancel our hydro walk, coming down and playing with soil and equipment, we're going to have to show it for you. So, first things first, we're going to look at some hydrometeorological equipment. So these are all elements of the water balance. So first we're going to start with the automatic weather station, which is here. So can you see that? And basically the elements of the weather station are to feed the Penman equation. So the Penman gives us the potential evaporation of a wet soil, i.e. an unstressed soil. And the components of that are basically heat. So we need to know some temperatures. We need to know the humidity, or more importantly, the relative humidity. And we also need to know the advective term, which is the wind speed. And if you put them all together in the Penman equation, then you'll get a calculation for Penman Monteith. So if you look at the top here, you can see something that looks a bit like a beehive, and we often call it that. It's actually a Stevenson screen. But in there we have two thermometers. One is measuring the ambient temperature, and the ambient temperature tells us how much water could be held in the air. And we also have another thermometer called a dew point thermometer, which is the actual amount of water that's in the air. So between the potential, because this temperature relationship is fixed, so long as we know the potential amount and the actual amount, the difference between them is the relative humidity. And I'll say more about that in the lectures. And I don't know if you can come around and look at the arm over here. Okay, so this arm sticking out, trying to get away from the shadows, is a radiometer, and that means we can measure the intensity of the radiation coming into the system. And that's, again, it's like the shortwave energy coming in, and then evaporation is in fact long wave energy. Anything else? So right on the top we have an ultrasonic rain gauge. So usually that would be some cups going round, an anemometer, but that's now replaced by an ultrasonic. So we've actually got three probes, ultrasonic beams going between them, and the wind actually slows down and attenuates that wind speed ever so slightly, and we can turn that both into wind speed and wind direction. So that's everything we need to feed into the Penman equation. The only thing we haven't got is the control of the dryness of the soil, which we'll do in a minute. So the version of that, which includes the plants and the roots, is called the Penman Monteith equation. Again, that's a potential evaporation. So if we move on to the rain gauges, so a typical rain gauge would look like this, standard rain gauge. It tends to have this nice, what we call a wine glass shape, and it also has this kind of sharp edge on the air, and they're all to kind of minimize the effects of wind. So we want the wind to go through. If it's straight-sided, we might get an issue with wind coming up. And the little sharp edge also cuts the wind and makes a little eddy. So in theory, all the rain should go into the middle. And so that's a standard tipping bucket rain gauge. If we delve inside one of these, you can actually see the tipping bucket. And so as the water drips through from the middle, it will fill up one of these capsules to a fixed amount, and then the weight of the water will cause it to tip. Hence tipping bucket. And then later on, that will also tip again. So this has been pre-calibrated to tip for every 0.2 millimeters of rain for every tip. So if we put a logger in here, or some sort of communications device, the only thing we're recording is these two magnets going past each other. So every time they go past each other, it makes a click, it gets recorded. So we record the time of the tip, and that we can turn into rainfall intensity. Okay, so that's kind of the industry standard and research standard. But we also have some rather archaic, older methods. So this is the Mark II rain gauge by the Met Office. I think there's some 4,000 of these spread around the country, all recording the volume of rain per day, and it forms part of our weather system, which you might pick up on the TV. So if you have a look at this, it's got the sharp edge. It's a little bit narrower. It's also straight-sided, which means it does suffer a lot from wind losses. If you look down the middle, we have something that drips through there. And then that goes down into this canister. Okay, which means that will fill up over a day if it's raining. You then pour that out into a graduated cylinder, and that will be a volume. The volume divided by the cross-sectional area will give you the depth, so we can get millimeters per day. So that's a manual rain gauge, and this is an automatic rain gauge. So this is good for volume. So if you have lots of these, we get a really good feeling for how much rain has fallen. And this one tells us how much rain has fallen. So we tend to use a mixture of these and these in our hydrometric network. And for the enthusiasts, maybe have a look at this small Calyx rain gauge around here. So you can get smaller ones, and they're quite cheap. So we're trying to make this more cost effective by getting more people making more measurements. And we often get our citizens communities to actually make these measurements, and we get some not perfect quality data, but lots of data, so we understand what did happen. Did it rain here? Did it not rain here? So that's really the two primary aspects of the water balance: the rain coming in and the evaporation going out. And that's enough of that. Thank you.